Hello, this is Magic 063 Differentiable Manifolds. I'm Kirill Mackenzie, and this podcast is about vector bundles. It's the first one, and I'm leading off by thinking about differential forms. Up to now, we've worked with differential forms as maps that take a string of vector fields and produce a smooth function. And for a lot of purposes, that's the best way to work. But it's also possible to consider differential forms as defined simply on strings of tangent vectors. And this is equally important. And I want to establish the correspondence between these. And the best way to do that will be by appealing to some vector bundle results, which we need in any case as part of the course. So just think back to when we started with one forms. We started by defining them as maps from the base manifold, the given manifold M, into its cotangent bundle, such that it's right inverse to the bundle projection C. So in other words, the value of one form at a point of M lies in the cotangent space at that point. And we also thought of them as maps from the tangent bundle to the reals, which are linear on each individual tangent space, TMM. So these are important ways of formulating differential forms, and what I want to do is extend this from one forms to K forms. So here's a preliminary version of the result I want. I'm calling it a pre-proposition. I've only written it for two forms, but the main thing is that this is a little bit informal. We could start with a map defined on tangent spaces or direct products of tangent spaces like this into the reals, which are bilinear and alternating, and which depend smoothly on the point M. And this indeed is one of the ways of setting up differential forms. But what I want to prove is that when we take a differential 2 form in the way that we've defined it in this course as a map that takes vector fields and produces a smooth function, then in fact for each point of the given manifold there is a unique such map. I'll temporarily denote it by underlining the omega and put in the subscript M, and it will depend smoothly on little m, and the actual if I take two vector fields x and y and I evaluate omega on them, then the value of that smooth function at a point little m is determined entirely by omega underlined at m and the tangent vectors x at m and y at m. So this will establish the equivalence of the 2 points of view, the two ways of formulating differential forms. And indeed, it's essential for what we want to go on and do. So, like I said a moment ago, the best way to approach this is in terms of a general result about vector bundles. And that's where we're going now. So the primary examples of vector bundles are, as you undoubtedly know, the tangent bundle and the cotangent bundle. There are many other bundles built on top of this. Of course, Tm leads to vector fields, T star M leads to one forms, but it's possible to build arbitrary tensors on M by combining these bundles in a way that we'll discuss a little later on. On the other hand, you could have something like a surface in R3, call that M, and you could consider the normal lines at each point. And this would give you a vector bundle over M. The disjoint union of all these normal lines would constitute a vector bundle over M. Or you could do something a bit similar. You could take a curve in R3, say unit speed, and you know you have the trihedron, you have the tangent vector. Let's assuming that it's non-zero at every point. It's a little bit wonky, but I hope you'll believe me, that's the tangent vector. And there's the principal normal, and there's the binormal. And these form, B for binormal. And these form a moving frame, a little R3 basis, oriented orthonormal basis, travelling around on the curve. And we could, for example, take the plane determined by the principal normal and the binormal, and that would give us a family of planes, one plane attached to each point of the curve, and that would be a vector bundle also. Or another example, final one for now, consider the Möbius band. So there's just the unit circle, say in the xy plane, viewed side on. And normally, of course, you think of the Möbius band as a thin strip. You take a long, thin strip of paper, give it a twist, and stick the ends together. But we can also consider that thin strip as not having a boundary. So it's an open strip around with a twist. And each of those little lines within the open strip could be taken, say, as the interval neg1 to 1 on the real line, and that would be that is diffeomorphic to the entire real line. So I can put a vector space structure on each of these little lines transverse to the circle, and that gives me a vector bundle structure on the Möbius band. So these are examples, and they're quite genuine and useful to visualize, but the fact remains that most vector bundles are of high dimension and can't really be visualized in any sensible fashion. And the best way to think of them is that it's a parametrized family of vector spaces, parametrized by the points of a manifold. So we'll go on to that. So I'm working up to the formal definition. This here is a slightly more... Oh, just a moment. Right, let's try that again. This paragraph here is a slightly more formal statement of what I said a moment ago. I'll just run through it. A vector bundle, E, on a manifold M, involves associating to each point of the manifold an abstract vector space, denoted E sub M, and these vector spaces must all be isomorphic to each other as vector spaces. And I've put down here something which is a bit cryptic in a consistent way. I'll come back to that much later, but might be best to ignore that for now. Let's put a line through that. It's quite true, but it needs explanation. These vector spaces must all be isomorphic as vector spaces to each other. And of course, all the data must be smooth. Now, there's a very small nuisance about standard vector spaces. I will usually take R, some Euclidean space, R to the, and I'll use little r for rank, as what I call the fibre type of a vector bundle. Sometimes it's better to take an abstract vector space V, and we'll do that too in due course. But the point about R to the R and V is that all of the EM are isomorphic to this R to the R or to this V, as the case may be. In fact, let's forget about V for the moment. We will come back to it. We'll just concentrate on R to the R. It's called the fibre type of the bundle, and R is called the rank. So here's the formal definition. A vector bundle consists of the following data: manifolds E and M, and a smooth surjective map, Q, called the bundle projection from E to M. A vector space structure on each fibre, that's each pre-image of a point of the bundle projection, such that there exists an open cover of M and charts for E of this particular form. Okay, so it's psi alpha. It's defined on U alpha cross R to the R. U alpha is a subset of M. R to the R is a Euclidean space, and the target is denoted E sub U alpha. It's the set of points of E for which the projection Q takes values in U alpha. I'll just write that again. Okay. And the further condition, is that for each point M of the manifold, if I hold M constant in psi alpha, then I get a mapping from R to the R to E to the M, and that must be an isomorphism of vector spaces. So that's it. A couple of points. First of all, it's very common to take the U alpha to be actually the domain of a chart for the manifold M, but there's no reason to do so. It's neither necessary nor particularly helpful most of the time. So U alpha could be some open set in M, open subset of M, which is not the domain of a chart. Another point is that these charts, these psi alphas, are certainly manifold charts for E, but of course they're of a special type. The domain is a product manifold like this. We haven't defined product manifolds yet. We will do, but I'm sure you can accept this for the time being. And secondly, there's the linearity condition in R to the R. So viewed from the point of view of E as a manifold, these are very special charts, but they are certainly manifold charts as well as being charts for the vector bundle structure. Another point to notice, if you look at Q in terms of a chart, then it's simply projection from that product to the first factor. And we haven't really talked about submersions yet, but that actually ensures that Q is a submersion. Okay, next thing. Fix a point of the base, say in U alpha, and I'll write psi sub alpha comma M for the map from R to the R to E of M, which is got just by holding M constant in the chart. Now this is an isomorphism of vector spaces because that's exactly part of the definition. So I can invert it, and I can compose it with psi beta M for another chart, beta, and what I get is a vector bundle, a vector space isomorphism from R to the R to R to the R. And these are two isomorphisms, so the composite is an isomorphism, and so that is actually in the general linear group RR. And I'm happy to regard GL either as matrices or as linear maps. We'll take each case as it comes. So this S alpha beta M, this is the definition, this S alpha beta M is a smooth map from U alpha beta at the intersection into the general linear group. It's called a transition function. I've got that down the bottom of the screen, but I'll come back to that. But the individual S alpha beta is called a transition function for these two charts, psi alpha and psi beta. And the point is that when you look at the actual overlap diffeomorphism, thinking of psi alpha and psi beta as charts for the manifold, then, of course, it's from this product U alpha beta cross R to itself, and it has this particularly neat form. The point M and a vector V goes to the point M, and V moved by the element of GL, defined by S alpha beta M. So that's a short check that I really strongly urge you to do. Then, if you think for a moment, you'll believe, I'm sure, that when you multiply these S's together in this fashion, the various terms cancel. So S beta gamma, I can think of that as beta inverse times gamma, or composition gamma. Then here I've got, well, it looks like I've got alpha inverse comp gamma, but I'm taking the inverse of that. So it's gamma inverse comp alpha. The gamma inverse cancels with the gamma here, and the alpha inverse there cancels with the alpha here. And lastly, the beta inverse at the front cancels with the beta at the back. And this is 1. And by 1, I just mean the identity matrix in the GL group. And this holds on any non-empty triple intersection. So the collection of S alpha betas are called a set of transition functions for E. And of course, if I take a different family of charts, vector bundle charts, then I'll end up with a different family of transition functions, but there's a sense in which it will be equivalent to the first set. And we'll come to that later. So this equation 117 can be neatly written like that. But one does need to remember that this multiplication and the inverse is being done pointwise. It's being done for each point M of the base manifold. Okay. This is a co-cycle condition, a non-abelian co-cycle condition. And of course I've written it multiplicatively because it is non-abelian, it's taking values in GL. So we'll come back to transition functions and co-cycles later on. They're crucial things for particular kinds of differential geometry and indeed for any sort of work with vector bundles. But for the moment, just a couple more basic definitions. Just a word about notation. When I want to be careful, I'll write EQM like that, but mostly I'll just say a vector bundle E, and that will denote the whole structure, not just the top manifold. So the simplest example, there's always these, is simply the product. Vector bundle, usually called a trivial vector bundle. So the structure is apparent. I don't really need to say anything about that. There's no, the transition functions are trivial. These examples do crop up. I mean, it's obviously simple, but it's an important special case. Then morphisms. A morphism of vector bundles over M. So this is assuming that I've got two vector bundles on the same base, E and E prime on the same base manifold F. Beg your pardon, on the same base manifold M. And a morphism of those is a smooth map F, which commutes with the bundle projections, and as a consequence maps each fibre of the domain over little m into the fibre of the target over little m, and that restriction is to be a linear map. Okay? And that's all there is to that. It's an isomorphism if it's a diffeomorphism, and it then follows that the inverse is an isomorphism also. We'll come later to consider morphisms of vector bundles when the base manifold changes. The definition is perfectly straightforward, but working with them is more complicated, and we'll come to that later on. So when I want to emphasize that the base is fixed, I'll call them base-preserving maps. And one last definition, and this may seem a little bit curious, but it'll become important later. A vector bundle is trivializable if it is isomorphic to a trivial vector bundle. And, of course, usually we identify isomorphic objects, isomorphic structures. But this is a case where isomorphic structures can be significantly different. It comes up in gauge theory, and it comes up in different other contexts as well. So this is an important distinction, and that's the word to cover it. Okay, that's the basics. There's another podcast following with more material on vector bundles.